So I said several formulas, and let me begin with the simplest of them. So first of all, remember we have a complex semi. I do not consider the real case. Also, it's also very interesting and exciting. So we have a complex semi-simple Lie algebra, finite dimensional. Maybe I will mention something about the infinite case today later, if we have time. And then there are so-called integral dominant weights. It is the following, if you remember. So the Lie algebra itself, G, is the sum of the Cartan subalgebra and one-dimensional root spaces, G alpha. And now for every alpha, there exists a canonical embedding of SL2 into G. Namely, there are, let me consider simple positive roots. Certainly what I'm going to do is possible not only for simple positive roots, consider simply positive roots. Alpha I. The number is equal to the dimension of H. And then I consider the elements HI, EI, and FI. HI can be also described as 2H alpha I divided by the inner square of alpha I. And EI and FI belong to G alpha and G negative alpha. And these three elements of the Lie algebra, they form a subalgebra of G, which is SL2. Moreover, I choose E alpha and F alpha in such a way that actually the commutator of EI and FI is HI, and HI EI is 2 EI, HI FI is minus 2 FI. So you see that this is the algebra SL2. At the moment I don't need EI and FI, but I do need HI, because now I can say that a linear map of H into C is called integral dominant weight, integral dominant, if lambda of HI is a non-negative integer. I'm not sure that this term integral dominant can be applied to the case when lambda is 0. I don't see that this case be any worse than any other case, but this is definitely, so sometimes it is written in different sources that lambda of HI should be non-zero, for at least for one HI. I'm not sure that this is really necessary, but let it be so. Now, what is important is that there is a classification of all irreducible finite dimensional irreducible representations of G. And this classification is done in terms of the highest weight. So if V is a representation of G, then a vector V is called a weight vector, non-zero, of the weight lambda if h v is equal to lambda of h v for every h in H. Now it is weight vector, highest weight vector. Is the same thing with the additional property that it is annihilated by the positive part of G, that is the subalgebra of G, which is the direct sum of all G alpha for positive roots alpha. Positive part. In the case of algebras like SLN, it is just the algebra of strictly positive, strictly upper triangular matrices. And then the facts which I don't want to write on the board, we discussed it several times, at least 2 times. That first of all, if V is irreducible, and finite dimensional, then there exists up to a constant factor precisely one highest weight vector. This is one thing. It can be extended. Whatever lambda we have, I do not suppose now this integral dominant. If you have any lambda, then there always exists a unique irreducible representation of G, not necessarily finite dimensional, but very much unique, with highest weight vector with the highest weight lambda. It is more or less trivial fact that irreducible representation cannot contain highest weight vector with different weights, only one. For every lambda such representation exists, and moreover I presented sort of construction here of this representation. And then this representation is finite dimensional if and only if the weight is integral dominant. So there arises a bijection, one-to-one correspondence between integral dominant weights and finite dimensional irreducible representations of G. Very strong facts with actually not very difficult proof. This we sort of know. So questions about this? No questions? So you agree with this? Good. Now I want to present several formulas, and let me begin with the simplest of them. Finite dimensional. Now, if something is finite dimensional, then there arises an actual question about dimension. And for dimension, there exists a formula, one of several formulas which are attributed to Hermann Weyl. First of all, I introduce a new notion. Rho is a common notation. Is the sum, 1/2 of the sum. This is the set of positive roots, alpha. So, half sum of all positive roots is denoted by rho. It is I do not play with this root. Although in cases which I know it is a root, but it is not important. Well, no, not a root. Absolutely. Yes. And now the following formula. I prefer to use this notation of capital lambda because I will need small lambda for different purposes. So this is the representation with the highest weight lambda. The right-hand side dimension means it is finite dimensional. So lambda is something. But the right-hand side is defined for any lambda. The sum over all product, excuse me. Product, all pi the roots. Here I write lambda plus rho alpha. And here I write rho alpha. What can be simpler than that? It is interesting that if, I don't know whether I find it interesting, but still it's sort of worth a short remark, that if lambda is not simple integral dominant root, then still this makes sense. Actually, maybe a complex number or real number or negative number, whatever. So in some sense, there exists a generalization of dimension to the case of an arbitrary weight, arbitrary lambda. And this actually also has some meaning in the representation theory. The representation itself may be very much infinite dimensional. But still there is some number, maybe complex, which can be naturally attributed to this representation as its dimension. You know, if we speak of groups rather than algebras, then what is the dimension of a space? This is, believe it or not, the trace of the identity operator. If you have a representation of a group, then certainly there exists such a thing. Maybe I will mention it for groups, I'm not sure. A character representation. You take an arbitrary element of a group, take the corresponding operator, and take a trace. There is a function on the group which is actually constant on every conjugacy class. There is a formula also for this character, which generalizes this formula in some sense. But if you specify that formula for the case when the element of the group is the identity, then you get the dimension. If the space is infinite dimensional, it's not quite clear what the trace is. Maybe with your qualification analysis, you can understand that there are different ways to attribute traces to operators acting in infinite dimensional spaces, even when actually the spectrum may be complicated, but still. Well, certainly it is not my subject. So I don't know it, and if you know it, that's okay. So this formula, let me make a couple of brief comments to it. Yeah, you have to brief. Example. Speaking of example, immediately we have in mind SL2. SL2. Rank is 1. So only one occupies the root, alpha. The Cartan subalgebra of this is this, with lambda 1 plus lambda 2 is 0. H1 if you prefer, but it's the only H is this. Now lambda is a function of this one-dimensional space. I mean one-dimensional. I can write lambda of lambda 1, lambda 2. Well, the sum of them is equal to 0, but it is not important. K1 lambda 1 plus K2 lambda 2. In particular, there is the root alpha. The only positive root, lambda 1 minus lambda 2. And its value on H, please make this computation, is 2. But now I consider lambda, and lambda of h is an integer. Well, positive integer, but not necessarily even. So lambda is not necessarily a multiple of alpha. It is a multiple of alpha over 2, right? Rho certainly also is alpha over 2 because only one positive root. Rho alpha is 2, excuse me. Certainly this vector 1 negative 1 has the inner square 2. They're usually in the product. So rho alpha is 1. The denominator in this formula, and I guess that dimension of v of lambda is actually lambda plus rho alpha, product of only 1. And this is if lambda of h is n, this will be n plus 1. We are familiar with this formula, so in this case, formula gives us what we know without any computation. We can do something, well, more than that. For example, we can take SL3 or SLN. Everything here is all the computations for classical layout is very simple. So if you have a SL3, for example, then there are 3 positive roots. I prefer to know them as alpha 1, alpha 2, and alpha 1 plus alpha 2. Rho, the sum of the 3 over 2, so rho is alpha 1 plus alpha 2. Rho alpha 1 is 1, rho alpha 2 is 1, rho alpha plus alpha 2 is 2. Now there are h1 and h2. You understand what they are. So h1 is this, 1 minus 1, 0, and 0 is here. h2 is the same with the shifted down. So there are 2 numbers, m1 and m2, 2 integers. And if you now, so this is lambda. This thing should be a function of m1 and m2. And if you look at that, well, this formula is not here anymore, but you remember it. So there is a product of 3 things, right? So we should take lambda plus rho alpha. If alpha is alpha 1 or alpha 2, then this is 1. And then divided by rho alpha. And this actually is m1. So this will be the following thing. Let me just write it. And if you believe, this is the following thing. 3, this is this lambda plus r alpha 1. This is m for alpha 2. This is for alpha 1 plus alpha 2. And we divide by 2 because the with rho alpha 1 alpha 2 is 2. So we have m1 and m2 are 2 positive integers, one of them can be 0. If both are 0, then this is something stupid. If no, something is wrong here. Here should be, the sum of these two, m1 plus m2 plus 2. Excuse me for this, it is easy computation. Now it is better. Now if m1 and m2 are both zeros, it is one-dimensional representation. For example, what happens if m1 is 1, m2 is 0? If you really plug this, you will get 3 as a result. 2 times 3. Can you imagine a three-dimensional representation of SL3? Yes, you can. This is the most natural three-dimensional representation. You can switch them. There will be another representation, actually dual to that. What if both of them are ones? If you plug this, it will be 2 times 2 times 4 divided by 2. If you are able to make this computation, it will be 8. Can you imagine an 8-dimensional representation of SL3? You can. SL3 itself is 8-dimensional. So this is actually the adjoint representation. It's dual to itself. Yes, but there are other representations. And this is the universal formula for their dimensions. Certainly, the generalization of this to any SL is immediate. For example, if n is very much arbitrary, we have SL n beta SL plus 1. We have SL plus 1. Then we can, so the weight will consist of n integers, right? If the first one and the last one is 1, and the middle ones are zeros, and you compute using natural generalization of this formula, compute the dimension, you will see this is the same dimension as Sn plus 1 itself, which is, so this corresponds to the adjoint representation. And so on. I don't know what else to say about this. So I said to you, and you can't believe it, you wish. I said to you that actually this formula can be obtained by specification to sort of a better formula, more general formula. It is so and not so. I mean, certainly there is a different formula which I will write on the blackboard immediately. This formula, the dimension formula, can be regarded as a special case of it, but with certainly some reservations. While character formula. First of all, character. Characters are defined for the representation of groups, the most natural definition. But since we consider Lie algebras here, it is sort of natural to begin with some other definition. So, I have my representation V lambda. V. Yes. And as we discussed last time, and it is very clear, the space is direct sum of weight spaces. So there are spaces V lambda of lambda. These two lambdas, I think they will not eat each other. So this is, and this space also has dimension. This dimension of this is the sum of all the dimensions. Actually, if we know the dimensions of these weight spaces, then it is right to say that we know everything. There are different ways to determine the representation, knowing its character. For groups, it is a procedure which is applied in canonical courses of algebra to finite groups. And everybody, I mean, instructor and students are all happy with that. But I consider the algebra. Let me write some cryptic character. I don't know, this is chi of lambda. First definition, what is this? Actually, what I need to know, I want to know these dimensions. And I write, this is the sum, dimension v lambda of lambda, and here I write e to the power lambda. And if you say that you do not know what e to the power lambda is, I can say only one thing. You don't need to know it. It is notation. It is a symbol. It is a symbol which satisfies the usual exponential property. E to the power lambda times e to the power mu is equal to e to the power lambda plus mu. So I use the symbol absolutely without any understanding that e is 2.7 and so on. So this is notation again, and what I prefer to know here is only one thing, namely that these symbols well obey the usual exponential rules. Then the following formula. Character maybe denoted as character of lambda is the following. First I write it, and then we can discuss what everything means. W small belongs to W big, epsilon of W. Here I write e to the power W of lambda plus rho, and I divide this over rho, and the product no, should no rho, e to the power rho. So as I said to you, I do not want to know what this exponent mean. Actually, simply the only thing that when I divide by e to the power negative alpha, it is the same as to subtract alpha from this. You understand? It is not too much. Now W.
Are the alpha all multiplying over all?
Alpha
positive,
certainly.
Okay.
Yes, excuse me. You're right. W, the Weyl group. It can be defined. I mentioned here somehow, but I can mention it again. Simply, there are simple reflections. If we have a root alpha, then negative alpha is also a root. And there are roots orthogonal, well, perpendicular to this root, and we simply the reflection in the plane perpendicular to the root alpha. So alpha, R alpha, rho alpha, I don't remember the notations. Reflection. H alpha, no, H alpha is there is canonical reflection which I don't remember. Maybe rho alpha. Which means that it is for any Euclidean space, there is such a notion as a reflection in the direction of a vector. So this vector alpha goes negative alpha, and there is a formula using. So what we do, we take the projection. So there is a plane orthogonal to alpha to my root. I take the projection onto this plane, then I subtract from this projection. So alpha goes in the negative alpha, the orthogonal plane is fixed, and this determines everything. this reflection of square is the identity, right? These reflections for all roots, non-zero roots, you're going to consider positive because for negative alpha we have the same reflection. This reflection for all roots, they generate a group. This group has properties, namely, it takes roots and roots. They are symmetries of the whole root system. This may be regarded as a different definition. So this is the group. It can be applied actually to any weight, right? Then epsilon of W, the group acts in a finite group for finite dimensional semi-simple reality. It's a finite group. So actually every transformation from this group has determinant plus minus 1. But say plus 1 or minus 1. And epsilon is plus or minus. If you prefer, every element of W can be presented as a product of reflections rho alpha. We take the minimum amount of these reflections which is needed for, they're actually arbitrary, and just consider its parity. For SLN, for SLN plus 1, this group is the usual symmetric group. And epsilon of W is the usual parity in symmetric groups. So this is plus minus 1. All the rest probably do not need any explanation. Now I want to say first something very much wrong and then small correction. Chi, you know, is contains full information about these dimensions. Hence, it should also contain the information about their sum. So we can say that knowing this formula, we can deduce the dimension formula from it. Now let me say this, it is true and false, more false than true, because if we do this, you will get 0 divided by 0 as a result of your computations. And then what physicists willingly do, you cancel what you can cancel, or you apply the L'Hopital rule, whatever you do. So in some way, you need to get rid of the zeros in the numerator and denominator by cancellation. And then you will get this dimension formula. This formula has very interesting generalizations. I'm not 100% sure. I have 16 minutes left, but I want to show, so I will not prove it. The proofs of these formulas are not very difficult. And if I had 3 or 4 more lectures, that I would have been able to do this all. If you find this formula with all these exponents sort of not convenient, I can show you another formula, which is certainly more convenient, and which gives a recursive way of computing all these dimensions. It is the following. So we have two things, lambda and lambda, right? Lambda is the highest weight. Lambda is just a weight. And also there is rho. Now the formula is the following. If you take lambda plus rho minus lambda plus rho and multiply it by the dimension of V lambda of lambda. Then we get the following, the sum. The sum is extended to all positive roots and also all positive integers. Well, quite a big sum, seemingly. And here I write lambda plus k alpha. Alpha dimension and this is the formula. In books it is called the Freudenthal formula. And my former topology students know this name because topological theorem proved by the same author, Freudenthal formula. Now look at it. And what's your impression? The first impression, very much wrong. It is absolutely useless because we have this dimension on the left-hand side, the dimension on the right-hand side, and what of that? We compare two things. But you see, lambda plus k alpha. Alpha is a positive root. K is a positive number. So the whole amount of weights, really lambda, highest weight, and the weights below, right? And if this is lambda, then this thing is over there, right? So actually, if we suppose that we already know dimension of the upper thing, which is 1, the upper space has dimension 1, generated by the highest weight vector, and that's all, right? Then this formula gives you some recursion, because to find the dimension of V lambda, we need to know the dimension of V lambda plus k alpha, so dimension of a thing which we can regard as known. If we go from the top to the bottom. This is also a very nice formula which certainly gives you all the dimensions. This also can be applied not only to the finite dimensional case, actually. Freudenthal certainly did it in finite dimensions. Now, probably I need to use the remaining 11 minutes to say something very frankly to you. So back to the beginning. We have G, we have H, and we have roots. We have simple positive roots. Alpha 1, alpha will be R prime, simple positive roots. Then there is a way to define a certain number, which is called Aij. This Aij is actually 2 alpha I alpha j, and here alpha I alpha I. These numbers attributed to Cartan. Cartan numbers. And this notation shows very much that they form a matrix. So Cartan matrix. What can be said about this? First of all, you can think that this matrix is symmetric, but actually it is symmetrizable. You see the division, if you replace Aij by Aj, you will have to divide by alpha j, and this may be a different number. So this matrix in general is not symmetric. Symmetrizable means the following. So this matrix C has the property that there exists a diagonal matrix D, so that the product is symmetric. So So we multiply, say, all the rows or all the columns the other side by some numbers. These numbers can be made integers. Very easy to understand what they are actually. You should multiply by. So if you take the diagonal entries being alpha I alpha I, then certainly the matrix becomes symmetric, and matrix is symmetrizable. In particular, Aij and Aji may be different, but it is impossible that one of them is 0 and one of them is not 0. So non-zero entries of this matrix correspond to each other. You can say more about this matrix. The diagonal entries are equal to 2. It's visible from this formula. Here, you have elements in non-positive integers. Non-positive integers. With this property of symmetrizability. Let me say that this matrix and Dynkin diagram contain precisely the same information. Namely, suppose we have a Dynkin diagram. Say this. AR. Then do the following. You draw a matrix. You write 1, 2, 3, 5, 2 on the diagonal. The amount of them should be equal to the amount of dots. Then if 2 dots are not connected by an edge, then the corresponding Aij will be 0. If they connected by a simple edge, you should write -1. For example, for this particular diagram, it will be this. And zeros here. And this is the Cartan matrix corresponding to this simple diagram, to SL n plus 1, SL6. SL6 in this case. Now, if you have double connection, which is possible, then it is the following. If this double connection is like this, so the inner product of this is 2 times less than here, right? So the corresponding element of the Cartan matrix will be bigger. You will be the following. The same here, 2, and here you will have -2 and -1. Or if the arrow goes the opposite direction, you should split them. If it is a triple connection, then certainly you write -3 and -1. So Dynkin diagram knows everything. Dynkin diagram is simply, you can say that this is a graphic presentation of a Cartan matrix. And now the very last thing about, by the way, we did here and we pretended that we did something incredible. But actually there are some properties of Cartan matrices which I listed. And my classification of Dynkin diagrams of simple Lie algebras is the same as the classification of such matrices. Full list of such matrices. No. On the condition that this matrix is positive definite, or rather it's after symmetrization, when it becomes symmetric, should be positive definite. So the matrix is positive definite after the symmetrization. Is the same as it is a Cartan matrix of a certain simple, semi-simple Lie algebra. What you can do, you can change the numeration of the roots, so you can make simultaneous permutation of columns and rows, and also you can say the matrix is irreducible if it cannot be made after this operation, simultaneous permutation of columns and rows, can be made this block diagonal. Now the last thing. I said to you that actually there are elements hi, fi, and ei in my Lie algebra. And now I can say more. These are generators of this Lie algebra as an algebra. Moreover, generation with respect to commutators, so you understand, no other operation. And moreover, it is very possible to list all the relations. They are the following. Ei fj is hi if I is equal to j and 0 if I is not equal to j. It is 1. Hi in j is a I j in j. And the same with f, only with minus. These are the basic relations. But there is one more relation which actually very easily can be deduced from what we know about series of roots. What happens when you commute is with f's? With is. Is with f is written here. Is with f, with is. And I say the following, that if we take ej and apply to it the commutator with ei and do it k times, then you get 0 if k is bigger than minus a I j. And this is actually this relation, the same for f. I do not write it, but I mean it. If you replace that letter either by letter, aij is negative. So negative aij is 0 or positive number. If you apply the commuting with ej too many times, more than then you get 0. And from the algebraic point of view, my Lie algebra is this. Is the Lie algebra with these generators and these relations. And now the last thing which I am going to say here in this room. What if we drop the condition? First of all, this can be applied to any Cartan matrix, an arbitrary matrix. Let it be without properties, twos on diagonals and non-positive integers north of diagonal, outside diagonal. But suppose that this matrix is arbitrary, that is not necessarily positive definite, then still the system of relations can be written. What we obtain is the so-called Kac-Moody Lie algebra. I can say that if the matrix is is positive definite, then the Kac-Moody Lie algebra, if the matrix is irreducible, is the same as a simple Lie algebra, simple fundamental Lie algebra. If the matrix is not positive definite, it's not so. Now, not positive definite. Can it be sort of close to positive, almost positive definite, but still not positive definite? Yes, this should mean that this symmetric matrix has all the eigenvalues except one positive, and this one is 0. And this one is 0. In this case, by the way, the matrix will be degenerate, which, by the way, can be easily deduced from this relation. Then, in this case, this Lie algebra has a center. This is what physicists usually call Kac-Moody Lie algebras, and they have a simple classification. They are, after factorizing over the center, there are two possibilities, but one of them which is easy to describe. You take a simple Lie algebra, a simple finite Lie algebra, and tensor it with the Laurent polynomials of one variable. You understand? C of t inverse. It will be another. Tensor product of Lie algebra and associative algebra is always Lie algebra. So you will get another Lie algebra, very much infinite dimensional. I can say that for Kac-Moody Lie algebras, and even in a more general definition, everything what we did can be somehow repeated. But many things become not true. For example, it's not true anymore, certainly it's infinite dimensional. Not true anymore that G alphas are finite dimensional, one dimensional. Finite dimensional, yes. It's not true anymore that if alpha is a root, then 2 alpha is not a root. So the root system becomes more complicated. But still, the main facts about representations, including all the calculus formulas, actually hold for Kac-Moody Lie algebra. Now I finish this, and as my final gift to you, I will send to you notes of my lectures in Stanford, which were precisely about representations of infinite dimensional Lie algebras. So they begin where we stop here. You can consider it as a continuation of my course, and if there were the second quarter, I certainly would have done precisely this. That's all, thank you. No. It could be much better.